Okay, so the sprint talks have 1 minute. Nikki, are you ready?
Yep.
Yep, awesome. Take it away.
All right. Hi, everyone. I'm Nikki Nielsen, and I'm a postdoc at Swinburne. So today I just wanted to highlight some new results from our soon-to-be submitted paper, looking at the intergroup medium of a compact group of galaxies at redshift 2.4. So we used the Keck Cosmic Web Imager to identify 4 galaxies in this compact group via their Lyman alpha emission. So these galaxies are about 30 kiloparsecs away from each other and about 30 kiloparsecs away from a background quasar. And the quasar spectrum features both a DLA and some rare ultra-strong magnesium-2 absorption, both of which are associated with this group of galaxies. So we did some photoionization modeling, some very detailed modeling, and looked at the metallicities of the clouds along the line of sight. We found multiple structures, including some supersolar metallicity outflowing gas clouds that are being driven by galaxy G1. We also found accreting gas clouds, likely falling onto the group, that are very metal poor. And then the rest of the gas clouds are likely to be intragroup material and then gas that's been tidally stripped from these galaxies. So if you're interested, feel free to contact me and ask some questions, or stay tuned for the paper, soon to be available. Thanks.
Thanks, Nikki. All right, Glenn, are you ready?
Yeah, good to go.
Great.
Hi, everyone. I want to talk to you about galaxy evolution through the eyes of the circumgalactic medium. In the first plot, I'm showing the absorption strength of Lyman alpha as a function of impact parameter. As you can see, the vast majority of galaxies do have H1 in their halos, but only a few do not. So why are these galaxies different? In the middle panel is an example of one such galaxy, which happens to be an edge-on Green Valley galaxy. It also has a quasar sightline along its projected major axis, which is great for probing potential gas accretion. However, this galaxy does not have any H1 absorption or metals at all, which is quite amazing. In the final plot, we show the absorption strength as a function of specific star formation rate. We see that star-forming galaxies always have H1 in their circumgalactic medium, which makes sense. Quiescent galaxies, some do and some do not. For our quenched galaxy, or a Green Valley galaxy, from our extensive analysis, we've concluded that gas accretion has halted and this galaxy is transitioning from star forming to quiescent through the Green Valley. If I had another minute, I'd tell you more about quiescent galaxies. If you love galaxy evolution, please check out our paper. Thanks.
Thanks, Glenn. Okay, Andrew, you ready?
Yep. Hello, everyone. Today I'm just going to highlight work I've been doing to understand dust attenuation as a function of cosmic time. So the motivation behind this is that we rely on correcting dust attenuation to derive galaxy properties. And so if it evolves, it has very important implications for how we derive our galaxy properties. And studies suggest that attenuation evolves with redshift, but these have really only been done at redshift 0 and redshift 2, and there's a big gap at redshift 1. And so to address this, I'm using HST GRISM surveys, namely WISP and 3D HST, which provides a sample of galaxies for which we can get Balmer decrements, which is sort of a gold standard dust indicator, and deriving their attenuation curves by combining that with their SED reddening factors. And so this is illustrated or demonstrated in the bottom left, where galaxies are getting progressively redder in their SEDs as a function of increasing values of their Balmer decrement. And the things that we actually observe are shown on the top right, which shows a similar trend. And from this, you can empirically derive the underlying attenuation curve, which is shown on the bottom right, which indeed does verify that there is an evolution in the normalization. As you can see, our curve, which is the red line, is in between the two curves at Z of 0 and Z of 2. This is sort of setting the benchmark for James Webb Cycle 1 program that I'm co-I on, to sort of do this in more detail to try and understand the exact source of this evolution. So these results will be presented in a paper that's soon to be submitted, so please stay tuned for that.
Thanks, Andrew. Finally, Femia.
Hi, everyone. So I just want to quickly present something I've been working on with some of the MUSE data. And that's been looking into the UV emission line morphologies at redshift 2 to 4 between helium, like for helium-2 emitters, between helium-2 and other UV emission lines, excluding Lyman alpha, of course. So on the left, you can see like a couple of example galaxies with the flux and then the signal noise contours. And you can clearly see that some of these galaxies do have extended emission in helium-2 going out of the PSF. So I started doing this assuming that it'll be like a quick thing to look at, but then it became a little bit more tricky because addressing the noise levels are quite complicated, especially in the XDF survey because of the orientation of the exposures taken. But just want to present these results, and you can also see the stacked profiles of about 12 galaxies with helium-2 emission on the right, top right. And it definitely gives you more signal noise, but the problem is then you're averaging out variation. So ideally, it's nicer to do it in individual galaxies. So that's what I'm currently working on, trying to understand the noise levels. And on the bottom right, you can see how the individual profiles and then the stacked one, which is kind of the bigger one on the bottom right. And if you squint your eyes, you can compare the helium-2 versus oxygen-3, 1661. And they kind of have all not same, but similar energy levels. So like if you expect the helium-2 to be powered by like normal stars, you should expect the profiles to also be along the same line. So this all falls into the category of trying to understand how helium-2 emission is produced, especially at high redshift galaxies.
Thank you. All right, thanks all. That was great. I'd encourage anyone that's interested to get in touch with the presenters over Slack as well.